In today's lesson, we are going to look at the area of composite shapes. So a composite shape is something similar to what we see below, and we'll get a more standard definition of it in a second. But what we want to do first is divide this shape up into 2D figures that we know. Now, there's multiple ways that you could do this, and everyone might have a different way. But if you're not sure, or you just kind of want to follow along, we'll go through it together. So if I want to divide this shape up, I could say, well, I see kind of half a circle or a semicircle here. So I can divide that up or just draw a line across. This is just, we're not changing the shape. This is just going to be for our understanding. So we're just going to draw a line across so we can see, okay, I do see a semicircle or a half circle there. Now, could draw a line straight down. Doesn't really give me any shapes, but it does help me break it up further into shapes that I can see. You can see here I have a rectangle, or it kind of looks like a square and a triangle. I could say draw a line across to have another triangle. Continue this line across. Now I have another triangle. I could, if I wanted to, I can draw a line down. Now I have a rectangle and an odd shape here. If I wanted to, I could draw another line across. There's another triangle. And then finally, there's another triangle. So I've divided this odd shape or odd figure up now into kind of the 2D figures that I'm familiar with, right? So our squares, we'll write them down, our squares, our rectangles, our triangles, and our circles. And with the circles, we have basically our semi or half circles, and maybe our quarter circles as well, depending on what our shape looks like. Right, but those are kind of the standard 2D figures that you want to look at dividing an object up into when you're given something that you're not familiar with. So as we get into more of our standard kind of lesson, the area of composite shapes, a composite shape is, or what they are shapes that are made up of two or more geometric shapes. So basically any combination or grouping of two or more geometric shapes into one larger shape. So again, we have our image here. That's an example of a composite shape. We saw in the last one how we would divide it up, or how we could divide it up into, again, those simple 2D shapes that we know. Because the reason we do that is, if we wanted to calculate the area, we need to break our composite shapes up into shapes that we know. And that's where we get those kind of those standard ones, those circles, those squares, rectangles, triangles. By breaking them up into those shapes, we can calculate the individual areas because we have formulas for those ones. We have standard formulas for those simple shapes. And then we either add or subtract the areas together to get our total area. Again, depending on what our shape looks like, we may have to add them together. We may have to subtract them if we've removed something. In the case of the example that we see here, we would have to add all of those shapes up. So let's take a look at a couple of examples together. So we want to find the area of the following shapes. So I have my shape here. Again, clearly it is not a standard shape. It is a combination of shapes or a composite shape. Now, to divide it up into shapes that I know, there's multiple ways that we could do this. We could draw a line across, again, just for our recollection or for our understanding, and now I have 1 and 2 shapes. You could divide it up in another way, such as this, where now I have 1 and 2 shapes. Again, either way is correct because you're dividing it up. You'll have the measurements available to you. You may just have to do different calculations on how to find it. I'm going to divide it up the first way, so we have shape 1 and shape 2. If I look at shape 2, I do need some additional measurements to help me figure out the area. Right? Again, because I'm dealing with what we have either rectangles or squares, I can see the area is going to equal length times width. If I look at the first one, that one's a fairly straightforward one. So the area of shape 1 is equal to length, which is 11, times the width, which is also 11. So it gives me 121 centimeters squared. Again, remember with area, our units are squared. For area of the second shape, or area 2, again, it's a rectangle or a square, so I can do length times width. Here I have one measurement, which is 6.5 centimeters. But I need to multiply that by another one, and I'm not sure what this measurement is yet. However, I can calculate it because I know the entire distance here is 18, and I know that the top part here is 11, so whatever's left over, or the difference between 18 and 11, is going to be the measurement of this section here. So this measurement here is 18 minus 11, which equals 7 centimeters. So this distance is 7 centimeters. So the area will be 6.5 times 7, which gives me 45.5 centimeters squared. To find the total area, now that I've found the individual ones, my area T, or my total area, is going to equal area 1 plus area 2, 121 plus 45.5, which equals 166 or 166.5 centimeters squared. So that is the area of this figure. If we look at the next one's a little bit more complicated because we're only given two measurements and their overall lengths and widths, or distances. So I have to use my understanding of what these symbols on this figure show to help us come up with the area, or at least the measurements of the individual shapes. Let's work on dividing it up. So an easy way might be to divide it up this way and draw a line on either end. So now I have a large square looking object and two squares on either end. Now in order to find the area, I need to come up with more specific measurements than this one here. Again, these figures on the lines, or on the shapes, these lines, they basically tell us that these sides have the same length. Same length or measurement. So basically this side is equal to this side, and this side, and this side, and this side, and so along on all of them. So all these sides are equal in size or length. And we can use that to help us figure out what is the total distance, or what is the measurement of each little section. Because we know the entire distance is 15 millimeters, and we can see that vertically we have 1, 2, 3 equal groupings, or 3 equal parts. If I take 15 and divide it by 3 to break it up into 3 equal parts, I get that each section is 5 millimeters, which means that each little tick, or each side that has a tick, is also 5 millimeters. So right off the bat, I have area 1, area 2, area 3. I can calculate the area of the two tiny figures on the side. It's still a square or a rectangle, so it's going to be length times width. So in this case, it is 5 times 5, which is 25 millimeters squared. Area 2 is the exact same thing, so I don't need to go through the full calculations again, but hopefully you recognize that they are the same figure. That leaves us with area 3. Area 3 we have no measurements for, except for, again, our large or our vertical side, because we know from the top to the bottom it's 15 millimeters. So again, so I know my length and my width. I know I'm going to have 15 multiplied by something. So I need to figure out what is just the horizontal distance here. Well, I am given the length from one end to the other, which is 18 millimeters. And I know that this little section here is 5, because I can see that above it has the same measurement, or the tick, which was 5. And on the other end, we have another one, 5 millimeters as well. So if the entire thing is 18 millimeters, and I take away 5 on either end, that leaves me with 18 minus 5 equals 8. So that means that this measurement here is 8 millimeters. So when I do my length times my width for my third object, 15 times 8, that will give me the area of this third object, which is 120 millimeters squared. It is also helpful to point out that even though it kind of looks like a rectangle, or sorry, a square, that may not always be the case. So we just have to be careful of that sometimes, right? Do not assume that the shapes are what they are unless we're either given the little tick marks to show that the sides are the same. Right? Make sure you actually do the calculations to prove or to verify what the actual shape is. Now that I have all 3 measurements, I can go through and find the total area. So it's the area of the first one plus the area of the second shape plus the area of the third shape. So we get 25 plus 25 plus 120 equals 170 millimeters squared. Now, that is the answer for this second shape, but there is another way that you could solve it. We're not going to go through it, but I will kind of briefly outline it just in case you want to go back and try it again another way, and just to verify that it does work. So we roughly have our shape here. We know our full distances is 18 and 15. Now you might say, well, I know the overall measurements if this was an actual full rectangle. So if you know those measurements, you could say, well, the entire rectangle would be area equals 15 times 18. And I would just have to take away the 4 squares in the corner. Right? We know they're squares because they share the same sides, or sorry, they have those ticks to indicate that the opposite sides are equal length. So I have 4 squares that I can remove. So my area total would be the area 1, which we'll put in purple, minus, let's put it in yellow, 4 times area 2, because there's 4 of them. Right? So that is another way that you could figure it out. Right? Again, that's the idea where you're subtracting the areas rather than adding them up. And again, different ways to visualize it. Neither way is more correct than the other, as long as you still come out to the same answer in the end. For the second one, is it possible to find the area of this shape a different way than you did the first time? Yes. Again, we kind of talked about that. We divided it up this way. You could have also divided it up this way. If we divided it up this way, we have still two shapes, but slightly different measurements. Area 1, we know is going to be 11 times, and now we need to figure out what this measurement is, rather than the other one that we found. We would do it the same way though. We know that the entire distance across is 11, and we know that we're taking up 6.5 centimeters of it for the one part, so the other part here has to be 11 minus 6.5, which gives me 4.5. So that means the area of the first one is going to be 11 times 4.5, which gives me 49.5 centimeters squared. And for area 2, again, 18 by 6.5. So again, no calculations needed to figure out any additional sides. 6.5 times 18 is 117 centimeters squared. So the total area is 49.5 plus 117, which gives me 166.5 centimeters squared. And if we go back up, we can see that it's the same that we got before. So again, different ways that you can do it or come up with a final answer, and they give you the same result in the end. So for 2, find the area of the following shapes. So we do have different shapes here, but again, you should have a formula sheet that shows the general formulas for those basic shapes that we know. So you just have to divide them up and go through and calculate what the area is for each of those individual shapes and then add them up. So I recommend pausing the video here so you can try these ones on your own, and then we'll come back with the answers. So if we come back to our two shapes, these are the answers that you should have. 504 centimeters squared for our first shape, the house looking one, and 237.86 meters squared for our dome looking object. So again, we use some different formulas. In the first one, we had to deal with the area of a triangle. So again, that was base times height divided by 2. Hopefully you could have calculated what the height was of the triangle when we divided it up by using the measurements given, because again, we weren't given the specific height of the triangle, and it was just a coincidence that it worked out to be the same height as the square. For our domed object, again, now we were dealing with semicircles, and I do realize that I have a small mistake here because I forgot to divide my shape by 2, because I calculated it for a full circle. However, we need it for half a circle. So I needed to take that one final measurement, divide it by 2, and get 76.93 meters squared, and use that in my final answer. So again, you can see there, just take your time with it. Double check that you are finding the actual shapes, and if they are half shapes or not the full amount, make sure you do the correct divisions for that. Again, with a circle, we're dealing with some new kind of terms. Hopefully you are familiar with them, but if not, in our formula for the area of a circle, we had pi r squared. Pi, again, is just a long repeating decimal. You could simplify it to 3.14 if you wanted to, or use the pi button on your calculator. Either one is fine. You may get a slightly different decimal number, but that's fine. R represents the radius, or from the outside of the circle straight to the center. And if we're not given that measurement, we could find it by understanding that the radius is the diameter divided by 2, or half the diameter. And the diameter is the distance from one side of a circle straight through the center to the other side. So in this case here, because we have our half circle, the length of the one side, or the flat side you could say, is our diameter. It goes from one side straight through the center to the other side. So if our diameter is 14, then that means our radius is 14 divided by 2, which is 7. Another thing to keep in mind when dealing with areas of a circle, make sure you use bed mass when you're actually calculating it. So what we have to do here, and this is why it's important to kind of revert back to our powers lesson, I have to do 7 to the power of 2 first, or 7 times 7, and then multiply that by pi. I can't do pi times 7 and then square my answer, because I'll get something different and I'm not doing it in the correct order. So keep in mind order of operations when you're going through questions like this. We do have another example, so this one's going to be a little bit different. But again, what we're going to do, I'll give you a chance to work on this one on your own, and we'll come back and take up or take a look at the solutions, and then we'll work together on the problem one on our own. So again, take some time to look at the first one up here. So we want to calculate the area, round our answer to 1 decimal place, and we're using the measurements that each grid line represents 1 centimeter. So take some time, pause the video to try that on your own, or you can kind of just watch through and follow along as I walk through the solution. So coming back and looking at this example, I've kind of done it a different way than what we've done before. Because we're dealing with a bunch of semicircles and quarter circles, and it'd be a bit harder to divide it up into shapes that we could add together, I had to do the reverse. So I imagined that I filled in or extended my lines or dimensions all the way to the end. So basically, assuming that none of those circles or parts of circles were cut out, what would be the area? So that's where I got this 4 by 7 to get a large area of 28 centimeters squared. So that would be this entire, oops, wrong color. That would be this entire object. That's the area of that entire space. What I then did is I realized that I had to subtract a half circle and 2 quarter circles. So I figured out the area of the half circle by using the radius in the formula, and I figured out the area of an individual quarter circle by dividing by 4 this time, still using the same radius of 2, and then I multiplied my final answer by 2 because I have 2 quarter circles. Now at that point you may have recognized, or even before, you may have recognized that these 2 circles, or these quarter circles and this half circle, they have the same radius. So if I have a full or half a circle and 2 quarter circles, I basically am removing a full circle. So you might have only done one area formula for the area of a circle with the radius of 2 and gone down and then started your subtraction. So you may have recognized that these sections that we're cutting out add up to a full circle. So rather than, again, calculate the individual parts, you could go through and just take away the full circle. But in the end, you should get an area of 15.44 centimeters squared. Moving on to a problem, so a little bit more of a challenge. So Michael is building a swimming pool in the shape of a rectangle with a semicircle attached to the short side. The dimensions of the rectangular part of the pool are 4.3 meters by 8.5 meters, and the pool is surrounded on all sides by a cement deck 1 meter wide. Michael wants to buy a pool cover that will just cover his pool. If the pool cover material costs $11.50 per meter squared, what will be the total cost of the cover? So here we need to think of a couple couple of things of what is the question asking us, because there's a lot of information here. So let's go back and highlight or underline or maybe put stars next to some important things. So Michael is building a swimming pool in the shape of a rectangle and a semicircle, so it might be helpful to know what shapes we're dealing with. The dimensions of the rectangular part are 4.3 by 8.5. The pool is surrounded on all sides by a cement deck of 1 meter wide. He wants to buy a pool cover that will just cover his pool. If the pool cover material costs $11.50 per meter squared, what would be the cost? So here, there's a lot of added information that we don't really need. Right? We don't really need too much about the cement deck because the pool cover is only going to cover his pool. So we're only concerned about filling in or covering this area. And we are given enough measurements to figure that out. Because we can see that I have area 1, a rectangle, and area 2, a semicircle, the two shapes that were mentioned. So the area of the first shape is length times width, 8.5 times 4.3. And I get, 36.55 meters squared. The area for my semicircle, again, pi r squared. Pi is 3.14, but I'm just going to leave it as the symbol. My radius is equal to half my diameter. So 4.3 divided by 2. 2.15, that's my radius. So we have pi times 2.15 all squared. Again, order of operations, square that 2.15 first and then multiply it by pi or 3.14. We get 14.51 meters square if we round it. So here the total area is equal to area 1 plus area 2, or 36.55 plus 14.51. And you should get a total area of the pool of 51.06 meters squared. Again, depending on how many decimal places you used and what your rounding was. So that's the area of the pool. What we need to know now is how much it's going to cost with that pool cover material. And I know that it's 11.5. So we'll say the cost is going to equal, we know it's $11.5 per meter squared. And if I have 51.06 of them, I'm going to multiply by 51.06 meters squared. And in the end, we should get a value or an amount of $587.19. So therefore, the total cost of the cover is $587.19. So that's the final thing that we need to calculate in terms of the question. So again, the main thing in this lesson is just being able to divide up composite shapes into the simple shapes that we're familiar with. Again, understanding that we may have to add those areas up or subtract them depending on the shape or the situation that's given, and then just being able to use those areas to help us solve some problems if we need to. And again, just make sure if you have trouble with those individual shapes, just to make sure that you are double checking your formula sheet and just taking your time to work through the problems.